In this video, we are going to learn how to find the center of mass and moments of inertia, two nice applications of our work with double integration, and another reminder of the connections between physics and calculus. Before we discuss center of mass, we first need to define mass using double integrals. In order to do that, suppose we are given a lamina, which is a two-dimensional distribution of mass in some sort of shape. The shape will typically be specified by a region R in the xy plane, and the distribution of mass will be defined by a density function using the Greek letter rho of xy, defined on R. So let's break this down for a minute. The object whose mass we're trying to find is called a lamina. It takes up a region in two space on the xy plane. Now, just to address, if we are talking about mass, there is some sort of thickness to this lamina, but we're going to assume that it is negligible so that we can focus on just the two dimensions that are covered by the region. And then the distribution, defined by the density function rho of xy, allows us to compute the mass if the density function is variable, meaning that it changes at every point in the region. With single variable calculus, we can go through this discussion. If there is a uniform density, meaning it would be the same at every point, now with double integrals, we can expand upon that and deal with variable density, where it changes at every point in the region. Combining all of these ideas, the mass of a lamina in the shape of a region R with density function rho of xy is defined as the double integral over the region R of the density function rho of xy dA. So mass is the little m, right? So mass, and breaking this down, we really are at the simplest levels talking about density times area. So mass equals density times area in two space. Three space, it would be density times volume. And we'll expand upon that later on once we cover triple integration. Now, as far as applications go, we're going to keep the discussion focused on mass. But if this function here represented charge, then this could represent the charge across the lamina. So there are other variations of this application. We're going to stick our conversation to mass. Find the mass of a lamina enclosed by y equals x squared, y equals 1, and x equals 0 with a density function rho of xy equaling to x squared y. So first let's draw our region just so we can see where we are integrating. So we only need the first quadrant. We have y equals x squared, y equals 1, x equals 0 is the y-axis, so here's our region. The intersection between those two curves would be at x equals 1. You could show it out algebraically, but I think we can agree upon that. Now this region could be defined type 1 or type 2 pretty easily. If we look at the density function, it doesn't push us in one direction over another. So let's define this as a type 1 region. So to compute the mass, we have the double integral. From bottom to top, we're going x squared to 1. Left to right, we're going 0 to 1. Density function is x squared y, dy dx. And now it's just a matter of integrating. So 0 to 1, 1 half x squared y squared. From x squared to 1 dx. So integral from 0 to 1, take the 1 half out. Then we'd have x squared minus x to the 4th times x squared would be x to the 6th dx. So we get 1 half times 1/3 x cubed minus 1/7 x to the 7th. Evaluate that from 0 to 1. So 1 half times 1/3 minus 1/7 is equal to 1 half times, so 7 over 21 minus 3 over 21 is 4 over 21, working with common denominators, and that will give us 2 over 21. So the mass of the lamina that takes up this region with the density function of x squared y is 2 over 21. And we're going to hang on to that value because we will need it in later problems. Now let's shift our discussion to center of mass. So the center of mass is the balance point of the lamina. So it's the point where we can perfectly balance the lamina in the horizontal direction. If the lamina has uniform density, the center of mass is the geometric center of lamina, which is called the centroid. And you may have heard that term before in a geometry class. So all this means is if our density function is constant across the whole lamina, then really what we're finding is the centroid as opposed to the center of mass. Computation is exactly the same, really it's just the terminology. To find the coordinates of the center of mass, which are x bar, y bar, so notationally we put a bar over x and y to indicate the center of mass, we must find the moments about the coordinate axes. The moments measure how the system balances with respect to each axis. So essentially we're going to weight the density at each point with its distance from either the x or y axes. Now, to do that, the x-coordinate measures position relative to the y-axis, and similarly, the y-coordinate measures position relative to the x. And the reason this is so important is we are going to see a little bit of variable interchange in the definition below, and this really helps kind of give us an understanding of why you're going to see that interchange. Okay, so x bar, which is the x-coordinate of the center of mass, we're going to compute that by dividing the moment about the y-axis by the mass. And the reason we're using the moment about the y-axis is the distance off the y-axis is the x-coordinate. Right? So in order to find the moment about the y-axis, we're using x-coordinates specifically, and that's why that's going to be part of the computation for x bar. So if we look at the actual double integral, we are multiplying the density function by x, so its distance from the y-axis at each point by its density, and then we're dividing it by the mass. Okay, so this is the moment about the y-axis divided by the mass. So it can be confusing because you see that subscript of y in a computation for x bar. If it really confuses you, then just skip over to the setup of the double integration where we are multiplying the density function by x. And then similarly for y bar, the y-coordinate of the center of mass, the moment about the x-axis divided by the mass, because from the x-axis the distance is y, and we're multiplying the density function by y, integrating that, dividing by mass. So this is moment about the x-axis over mass. And this computation here builds off the average value computation we did earlier for double integrals, where we took the double integral of a function and then divided it by the area. Well, now we're taking a function, which is in this case x times the density function, and then dividing it by the mass, which is finding an average, the same way we found average value earlier. Okay, so this computation didn't come out of anywhere, it really built off something we spoke about earlier. So let's use that same example as before, but now finding the center of mass. So we don't need to draw the region, we know what that looks like. So let's start with our moment about the y-axis. So we're starting the process of finding the x-coordinate of the center of mass. So that's going to be double integral from x squared to 1 from 0 to 1. And we're multiplying the density function by x. And I don't need to write rho of xy, we know what that is. So that's x squared y dy dx. Right, so this x is the new addition to our double integral to find the moment about the y-axis. Simplifying what's inside of our double integral, we would get x cubed y dy dx. Integrate that, so 0 to 1, 1/2 x cubed y squared, evaluated from x squared to 1 dx. So we get 1/2 integral from 0 to 1 of x cubed minus x to the 7th dx. So 1/2 times 1/4 x to the 4th minus 1/8 x to the 8th. Evaluate that from 0 to 1. So 1/2 and then times 1/4 minus 1/8 is 1/2 times, so 2/8 minus 1/8 is 1/8, 1/16. And we're going to need that value to find the x-coordinate of the center of mass. We'll hold off for a moment. Let's find the other moment about the x-axis, and then we'll do both coordinates of the center of mass at the same time. So now we'll find the moment about the x-axis. So integral from 0 to 1, integral from x squared to 1. If we're going off the x, we're multiplying by y, x squared y dy dx. So there's the new piece here. So that's going to be integral from 0 to 1, integral from x squared to 1 of x squared y squared dy dx. The steps for integrating are going to be very similar, so I'd rather focus the discussion in this video on the new elements of center of mass and later moments of inertia than the process of integration. So here we should get 2/27. By all means, use this as a practice problem for your double integration and confirm that you do in fact get 2/27. So now shifting our focus to computing the center of mass, so x bar then is the moment about the y-axis over the mass. And if we remember, the mass for this example was 2/21. Okay, so we have the moment about the y, which was 1/16. Instead of dividing, I'll multiply it by the reciprocal of 21/2. So 21/32 is x bar, or the x-coordinate of the center of mass. Y bar, we're taking the moment about the x-axis, dividing it by mass. So 2/27 times 21/2. We do get some reduction here. The 2's reduce, and then the 21 and the 27 reduce. So we get 7/9. So that gives us a center of mass, which is x bar, y bar, at the point 21/32, 7/9. So that's the point at which this particular lamina would be perfectly balanced. Another way to think of it is if we concentrated all the mass at this particular point, that point mass would have the same moments as the lamina that we've been working with in these examples. Okay, so now that we've established center of mass, let's talk about centroid. So find the centroid of a lamina enclosed by y equals x plus 1, y equals 1 minus x, and y equals 0 with a uniform density function. Okay, so drawing out our region. So we have y equals x plus 1, y equals 1 minus x, and y equals 0. So we have a triangular region. Uniform density function means that rho of x, y is equal to a constant, which we will call k. So at every point in this region, the density is the same. It's a constant value we're calling k. This region is going to be easiest to define as a type 2 region, so going from left to right, which means we do need to convert the bounds. So this will be x equals y minus 1, and this will be x equals 1 minus y. Okay, so we need mass and then 2 moments. And then we can put all that together. So mass, I'm going to avoid putting the bounds in for a second, and you'll see why. So over the region R, density function is k dA. Now because k is a constant, I can factor that out. Double integral of r dA, and this is really 1 times dA. If we recall, the double integral of 1 dA is nothing more than area. So we can actually do this problem, for mass at least, without any integration, because our region is a triangle whose area we can find with a formula. So the area is 1/2 the base, so -1 to 1 is 2. The height is 1. So the area is 1. So k times 1 equals k. And I chose this problem in particular because we do avoid integration for a few of these computations. Okay, so now that we have a mass, which unsurprisingly is k, since it's the density at every point is the same, let's talk about x bar next. I know I'm skipping over one of the moments and going straight to the coordinate of the center of mass, but you'll see why. So x bar is going to be 0. And that's for two reasons, two important reasons, and they both have to be true. First, the region defined by this lamina is symmetric about the y-axis. Right, so region R is symmetric about the y-axis. And then we're going to combine that with the fact that the density distribution is also symmetric about the y-axis. In this case, the density is uniform. So the density distribution on the left side of the y-axis is the same as it is on the right. Okay. The density distribution, we'll just say density, is symmetric about the y-axis. Right? If those two things are true, we can assume that the coordinate of the center of mass, in this case the x coordinate, is 0. Right? So we need symmetry in the region that's defined by the lamina, and we need symmetry in the density distribution. It doesn't have to be a uniform distribution for this to be true. Right? If an equal amount of that density is distributed on the left side of the axis as is the right, and you can convince yourself of that, then we can make the assumption that the coordinate is 0. If you can't convince yourself, then go through the process of integration. So now that means that the centroid is going to be on the y-axis, and if you remember from geometry, the centroid is the intersection of all of the medians, and they intersect at a ratio of 2 to 1, or they break each median into a ratio of 2 to 1. So we should expect the centroid, in this case, to be at 1/3, just looking at the triangle, 1/3 or 2/3, but in this case, we should expect it to be 1/3. But let's confirm that with calculus. So we're going to find the moment about the x-axis. Okay, so we decided that this is a type 2. So we're going from y plus 1 to 1 minus y, and then from 0 to 1. Now, again, less concerned about the integration in this video, so if we integrate all this out, we would get k over 3. And actually, I missed a piece. Hold on. Let's back it up a second. K times y dx dy. We need that factor of y being the distance each point is from the x-axis. That would have been bad. So that's equal to k over 3, which means then that y bar is k over 3 divided by the mass, which is times 1 over k. So we get 1/3. So that means the centroid in this problem, because it's a uniform density distribution, the centroid is the point 0, 1/3, which does in fact confirm that geometry result that we learned in high school geometry as well. Right, so practice your integration. Right, you should get k over 3, and then the new element, which is finding the centroid in this example, is going to be at the point 0, 1/3. Okay. Now let's continue our discussion talking about moments of inertia. So the moment of inertia measures how difficult it is to spin the lamina about a given axis. For a point mass, the moment of inertia is the mass times the square of perpendicular distance to the axis of rotation. So you may have seen in physics, I equals mr squared. I is the moment of inertia, m is the mass, r is the perpendicular distance to the axis of rotation. R kind of makes sense because we are talking about a radius, since if we were to spin about an axis, we would create a circular path. So for a lamina, extending it now to our work with double integrals, we integrate the product of the density function at a point and the square of the distance from that point to the axis of rotation. So essentially we're going around to each point in the region, taking the density function at that point, and then squaring the distance from the axes of rotation. So if we look at the double integrals set up below, so the moment of inertia about the x-axis is the double integral over the region R of y squared times the density function. Right, so this is the moment of inertia about the x-axis. Remember, distance from the x-axis is the y-coordinate of each point, so we're squaring y, multiplying it by the density function. Again, that y squared, think of radius squared if you had that circular path, if you were actually to start the motion. Then similarly, the moment of inertia about the y-axis. Distance from the y-axis is x, so we're squaring the x-coordinate, multiplying it by the density function. That gives us our moment of inertia about the y-axis. And then the last one down here, with the subscript of 0, that's our polar moment, or moment of inertia about the origin. So if we want to start rotation about the origin, and that's the sum of the other two moments of inertia. So if we add the moment of inertia about the x to the moment of inertia about the y. And really, we are dealing with 2 space, but if we were to extend into 3 space, really what this is saying is rotating about the z-axis, but in the xy plane. Right? So that's why we talk about a polar moment or the moment of inertia about the origin. Okay, so find the moments of inertia of a lamina inside the circle x squared plus y squared equals 9, below the line y equals x, and above the line y equals 0, with a density function rho of xy equaling to x times y. All right, so new region, so let's draw this out. We're above y equals 0, circle, so I'll draw the upper half of this circle. So from -3 to 3, y equals 0, we're good there, and y equals x. Okay, so we're looking at this sector of the circle right here. Polar is going to make a lot of sense here as far as defining our integration. Y equals x defines the angle theta equals pi over 4. If you forget that, remember you can replace y with r sine theta, x with r cos theta, turn it into a tangent equation, and solve. One of your solutions will be pi over 4. And while we're converting everything, the density function is going to be r cos theta times r sine theta, which is r squared cos theta sine theta. Okay, so moment about the x-axis, double integral of y squared. So we'll jump right into polar. So y squared is going to be r sine theta squared times the density function, which is r squared cos theta sine theta. And then dA, which in polar is r dr d theta. So just breaking this down again, y squared times the density function, dA. And then as far as the polar bounds, we're going from 0 to 3, 0 to pi over 4. Okay, so this is going to result in a separable double integral because we have r squared times r squared times r, so r to the 5th times sine cubed cos theta. So let's avoid an intermediate step and just go straight to separating. So integral from 0 to pi over 4 of sine cubed theta times cos theta d theta times the integral from 0 to 3 of r to the 5th dr. So integrating with respect to theta, underline sine, that would be our u in a u substitution. Derivative is cosine, that would be the du term. So we are going to get sine to the 4th theta over 4. Evaluate that from 0 to pi over 4. And then times 1/6 r to the 6th from 0 to 3. So we are going to get square root of 2 over 2, so 1/4 square root of 2 over 2 to the 4th minus 0, and then times 1/6 times 3 to the 6th. Okay, so that's really 1/4 times 2 times 2, so 4 over 16. And then here we can reduce by a factor of 3, just to make life a little easier. 3 to the 5th is going to be 243 over 2. And then here the 4's reduce, so we get 243 over 32. So that's the moment of inertia about the x-axis. Now about the y, moment of inertia about the y. So same bound, 0 to 3, 0 to pi over 4. Now we're multiplying by x squared, since x is the distance off of the y-axis. So r cos theta squared. Density function, r squared cos theta sine theta. And then r dr d theta. So remember x squared, rho of xy, and then dA. Again, separable, so 0 to pi over 4. Now we'd have cos cubed theta sine theta d theta times the integral from 0 to 3 of r to the 5th dr. Now saving us some time and effort here, I've done this ahead of time, so that's 729 over 32. So now we have the moment of inertia about the x and the moment of inertia about the y, so that makes the polar moment 243 over 32 plus 729 over 32, or the sum of the two moments, and that's going to be 972 over 32, which does reduce to 243 over 8. So those are all three moments of inertia that we can find for this particular lamina, about the x, about the y, and then the polar moment, which is about the origin. Okay, now one last concept to cover here, and if we recall for a point mass, the moment of inertia is I equals mr squared. We defined that in a previous slide, where r is the perpendicular distance to the axis of rotation, also called the radius of gyration. So now we are focused more on the r value being the radius of gyration, and that tells us the distance from a given axis that we should locate a point mass m so that it has the same moment of inertia I about the axis as the original lamina does. So essentially, how far off the axis do we have to go to locate a point mass, if we concentrated all of the density there, that would have the same moment of inertia? Right? And to find the radii of gyration, really what we're doing is taking I equals mr squared and solving, right? R squared equals I over m. R would equal the square root of the moment of inertia over the mass. So for our purposes, notice the double bar notation. The radius of gyration about the y-axis is x bar. So that's the square root of the moment of inertia about the y over mass. And then y double bar, which is the radius of gyration about the x-axis. That's the square root of the moment about the x-axis, moment of inertia, I should specify, over the mass. Okay, so let's look at that same example, and now just finding the radius of gyration, or radii of gyration, I should say. That means we do need to find the mass. So same bounds, so 0 to 3, 0 to pi over 4. Now we're just integrating the density function, so r squared cos theta sine theta, and then times r dr d theta. And again, similar theme to this video, let's not do all of the integration out. This would give us, let's see, I wrote this ahead of time, 81 over 16. It's separable, same steps as before, but now that we have that value, let's focus on the more relevant conversation. So x double bar, which is the radius of gyration about the y-axis, we're going to take the square root of the moment of inertia about the y-axis, which was 729 over 32, divided by the mass, so multiply by 16 over 81, the reciprocal. We do get some reducing here, so 1 and 2, and then the 729 and the 81, that would be 1 and 9. So this is really the square root of 9 over 2, which is 3 over the square root of 2. And then the radius of gyration about the x-axis. So we're taking the moment about the x, which was 243 over 32, and then multiplying or dividing by the mass, which is multiplying by 16 over 81. Again, some reducing here, 1 and 2, and then in this case 1 and 3. So that's the square root of 3 over 2. So the radii of gyration, 3 over rad 2 for the x, or for the y-axis, x double bar, and square root of 3 over 2 for the radius about the x-axis, or y double bar. So a lot of interchange between x and y, as I told you there would be earlier in the video, but we've gone from mass to center of mass into moments of inertia and concluded with radii of gyration. Right? As with everything, practice and looking back at these definitions is going to be extremely important, and I'll see you in the next video.